An epic crane catastrophe wrecks a Milwaukee ballpark.
You knew that there were people up on the structure that couldn't have survived.
A bridge in Washington state sinks like a ship.
When the Hood Canal Bridge rolled over, that was a real eye-opener.
A stadium roof comes crashing down in Connecticut.
This came within hours of being one of the biggest calamities in the history of American structural engineering.
And a devastating dam disaster stuns the UK.
This engineering catastrophe cost lives.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. Engineering catastrophes can strike at any time. Some oversights take years to develop into a problem. Other failures can turn into tragedy in an instant. Like this construction disaster in Wisconsin in the US.
This was a unique project with unique problems.
A build that pushed the limits to the edge and beyond.
The margin for error here was just too small.
This disaster resulted in terrible tragedy.
The cables started to squeal. There were a couple of loud bangs. I looked at Lance and I said, time to run.
Milwaukee, on the western shore of Lake Michigan. In its early days, the town served as a trading post. But in the 1840s, settlers arrived from Germany and began to do what they do best: brew beer.
Milwaukee is known as Brew City. The city's passion for brewing dates back nearly 200 years.
Beer is not all that this city is passionate about.
Its love of baseball runs just as deep, with their major league team aptly named the Milwaukee Brewers.
And this is the epic home of the Brewers, Miller Park. It's been a mecca for the team's fans for decades, like local journalist Jim Nelson.
People love coming to Brewers games and tailgating in the parking lots surrounding Miller Park, cook out, drink beer, play Frisbee, have a great time.
Built in the 1990s, the mammoth Miller Park was one of the largest construction projects in Wisconsin history. But engineers weren't just building an average ballpark. In a region with unpredictable weather, the goal was to draw bigger crowds throughout the entire baseball season.
Milwaukee has warm, humid summers, which are perfect for baseball. But the season starts in spring and runs all the way through to autumn, when the weather is much less predictable.
The only way to guarantee constant play in Milwaukee's erratic weather was a closing roof.
The retractable roof allows certainty for days like today, when you're coming to a baseball game and you know they're going to play.
Closing roofs are nothing new, but this one would be unlike any other in the world.
The engineering solution was a pioneering fan-shaped retractable roof that could sweep closed from either side to mimic the shape of the baseball field below.
Engineering consultant Christopher Pinto worked on the stadium.
This was a totally different take on retractable roofs. No one had really done something like this before in the United States, to create a fan-shaped roof of 5 different moving panels that could all move separately, that all stacked over one another.
In 1999, 3 years into construction, the time came to install the unique roof. This epic lifting job demanded an equally epic machine.
This was a heavy lift and called for one of the world's largest construction cranes, known as Big Blue.
Big Blue, a 170-meter tall heavy lift crawler crane, capable of elevating up to 1,500 tons, was the monster machine brought in for the job. Not only could this crane lift the massive loads required, it could also maneuver the complex roof sections into place with precision.
A fundamental rule for lifting heavy loads is for the crane to maintain equilibrium. Basically, it has to be perfectly balanced.
Big Blue maintained its perfect balance until July 14th, 1999, when its team faced one of the most challenging lifts of the project.
Big Blue had been on site for 11 months and had successfully hoisted 10 roof sections into place, but this large curved panel was one of the heaviest components and a really complex lifting job.
The roof sections to be lifted that day weighed more than £1 million.
The epic lift caught the attention of crane enthusiast Bob Winkle and amateur photographer Lance Wallace.
I'm driving on the freeway, I'm trying to look at it while I'm driving, but I can't focus on the road either.
And we pulled up by the old park.
So this is about where we parked, and I started shooting pictures. And we were standing next to about 10, 15 other spectators.
The lift was also being filmed by a safety team that was carefully monitoring every aspect of the operation. With a lift like this, safety is paramount.
With every load, calculations are done to ensure that the height, the distance, and weight of the lift all allow a safety margin. And one other crucial element to the equation is the wind.
The day was pretty windy. It started out in the morning, they were having some heavy gusts, and there were questions as to whether they were going to do the pick. And when we came back through at 4 o'clock in the afternoon, they had it up in the air, and that's why we had to stop and actually see what was happening.
Suddenly, something unexpected began to unfold.
On the drums for the cables, you could hear that, and they started to squeal. There were a couple of loud bangs. They were primarily explosions. And at that time, I looked at Lance, and he said, "What was that?" And I said, "Time to run."
The massive crane started to fall. Big Blue had collapsed, smashing into the stadium below.
Its center window, the third one, is where primarily everything went through.
During the collapse, there was pieces flying through the air. It was like tension being released in the metal and just small explosions that just kept happening.
The scale of the damage was devastating, and not just to the structure of the stadium.
When the crane fell, I personally thought that, yeah, people had to be injured and we had to have deaths, because seeing one of the baskets get swung out of the way, and he was actually saved, but you knew that there were other people up on the structure that couldn't have survived.
Most of the construction team narrowly escaped with their lives. But a second crane helping to direct the lift was also forced to the ground. Tragically, 3 men lost their lives. After the catastrophe, engineers examined the scene to discover what had gone wrong. Investigations revealed a combination of factors had caused the collapse, including a last-minute change to the crane's position.
Stability is an absolutely critical part of crane operations. It's vital that the ground is sufficiently strong to support the crane.
Contractors noticed ground cracking around Big Blue, so they moved the crane to more stable ground. But an existing part of the roof was now blocking the path of the new panel.
The crane moved to a new position to facilitate the lift, but the roof structure had to be lifted higher than initially planned, to about 350 feet or 100 meters above the ground surface.
Lifting the roof section higher than planned increased its exposure to the already high winds. Far from ideal, given the section of roof that was being raised.
The size and shape of this load was a major factor in the accident. It had a surface area larger than 3 jumbo jets, and it was curved like a giant sail, all of which made it very vulnerable to the wind, with a phenomenon engineers call the wind sail effect.
The unusual load, combined with the wind, was more than Big Blue could handle.
The crane was subjected to sideways forces that it simply wasn't designed to withstand.
With a crane so close to its safety limits, only one thing had to go wrong to trigger a snowball effect, and there was nothing anyone could do to stop it toppling over.
Big Blue was completely destroyed in the accident. As plans were laid to continue construction, engineers were determined to learn lessons from the tragedy to ensure that nothing like this could ever happen again. The 1999 collapse of Big Blue set the construction of Miller Park back by an entire year. High winds combined with the increased height of the lift and the sail-shaped load pushed Big Blue off balance, and the excessive sideways forces broke the crane in two. But the ambitious build had to continue.
Clearly, no one wanted a repeat of the tragedy, so the roof design was modified and a different crane brought in to finish the job.
Miller Park opened for its first game in April 2001. Positive change did come from this tragedy. Crane safety was forever improved.
The investigators proposed a raft of safety measures, including changes to the planning processes, positioning of the observers, and better monitoring of the wind conditions at key points on the crane.
Big Blue set a new precedent in regulations that now safeguard construction workers worldwide. To this day, the 3 steel workers who died during this terrible accident are remembered by the city of Milwaukee. Engineers have to take into account everything that the elements might throw at them, but sometimes even the most solid structure can fall victim to Mother Nature. Like this bridge in Washington State that was destroyed by a string of failures.
When designing any structure, engineers have to consider Mother Nature.
A vanishing roadway that cut a vital transportation link.
I have seen many interesting things in my life, but when the Hood Canal Bridge rolled over, that was a real eye-opener.
This was the perfect storm, and it revealed a catalogue of engineering errors.
Northwest Washington State is an unspoiled wilderness.
This is a pretty remote and wild part of America, surrounded by mountains and buffeted by the Pacific Ocean. The landscape is splintered by waterways carved out by ice thousands of years ago.
With all this water, dozens of communities have long depended on bridges. Norma Tipton has lived here for decades.
It's great to live here because I think it's one of the most beautiful areas in the world. We do rely on bridges a lot because there's so much water around.
And this is one of the most unique. The William A. Bugg Bridge. When it first opened in 1961, this was one of only 3 permanent floating bridges in the world, and it was an immediate hit with the locals.
It's the only link for people who want to get from Jefferson or Clallam County over to this side and to Seattle, which is, of course, the biggest city in the area.
Although officially named the William A. Bugg, this bridge is better known for the piece of water it spans, the Hood Canal.
The name is misleading. Hood Canal isn't actually a canal, it's a fjord, a narrow, deep valley cut by a glacier and then flooded by the ocean. It's about 1.5 miles or 2.4 kilometers across, but a massive 50 miles or 80 kilometers long.
At the time, nearby Seattle was home to the world's longest floating bridge, successfully spanning Lake Washington. But crossing the Hood Canal was a whole new challenge.
The fjord is 347 feet, or more than 100 meters deep. That's far too deep to build a bridge with legs. At that length, they would need to be impossibly wide to be strong and stable enough. And building a suspension bridge would be astronomically expensive, and so a floating bridge is what made the most sense.
The bridge would be supported by a series of 23 concrete pontoons, held in place with cables and anchors on the seabed. Although made of concrete, the pontoons float because they're hollow like a barge. The bridge deck sits above on elevated trusses. It may sound like a simple idea, but it was hugely ambitious, as State Bridge Engineer Patrick Clark explains.
The canal at that time was unusual, and it was the only floating bridge that had an elevated roadway all the way across. And the reason for that, the waves are much bigger on Hood Canal than they are on Lake Washington. So with the high elevated structure, traffic's able to travel along with wave spray basically passing underneath.
And it needed its elevated status because despite being deceptively calm, on some days this fjord can be anything but, as winds roll in from the nearby Olympic Mountains.
Although a long, narrow fjord might seem like the perfect sheltered harbour, in certain conditions the Hood Canal is almost the opposite. It acts like a giant wind tunnel, focusing high winds along the valley, which whip the ocean up, creating huge waves, and the Hood Canal Bridge lies right across their path.
As well as withstanding these unpredictable conditions, this floating bridge had to be engineered for another purpose.
The US Navy has had a base on the Hood Canal since the Second World War. It's now used by the Pacific Submarine Fleet. So, when the bridge was built, for reasons of national security, it had to be able to open wide.
While most opening bridges lift or swing, this one retracts or withdraws, referred to as a draw span. The design incorporates two floating sections in the center of the bridge that can be withdrawn back towards each shore. When fully retracted, a 180-meter gap in the middle allows large naval vessels to pass.
The draw span is a great solution for letting marine traffic through. But in an area of high winds, strong tides and currents, you're left with two very long floating jetties, each of them much more vulnerable to sideways forces than if they were permanently connected.
For 17 years, the bridge battled Mother Nature and slashed journey times across the Hood Canal. But an unexpected weakness was about to be dramatically exposed. On February 13, 1979, a storm rolled from the Pacific Ocean into Washington's Hood Canal.
I think that this was a once-in-a-lifetime windstorm for this area. I don't remember any nearly as severe as that. And the sky was quite dark, and there were big white caps all over the canal, and the trees were waving like crazy, whooshing wind through.
To protect the bridge, the drawspan was opened.
And when you build these big, heavy draw spans, they draw a lot more load. But when the storms start to come up, we shut it down to traffic, and we retract the draw span back onto each side, so we leave a 600-foot opening. It relieves the pressure from the wind and waves on the bridge.
Experts calculated that hurricane-force winds were blowing up the fjord, exceeding 120 miles, or nearly 200 kilometers an hour. There was also a strong current flowing in the opposite direction. Working together, they battered the bridge.
The pounding appeared to be more than the bridge could handle.
I had a friend who lived near here, and she called me and said, "Norma, can you see the bridge?" And I said, "Yes." She said, "It's going down." So I walked over to my big window and looked out. It just rolled over.
At around 7:30 a.m., the floating bridge broke free from its anchors, rolled over, and sank.
It went, it was really a few seconds, but we could really see it.
The bridge was at the bottom of the fjord. The crossing had been closed before the storm hit, so luckily no one was hurt. But in a region known for its extreme weather, why had the bridge failed so catastrophically?
With nearly half of the bridge's 23 pontoons sunk, residents and officials were left asking, how did this happen?
Investigations revealed that the perfect storm, both in terms of weather and engineering failures, had hit the bridge.
So when the storm came on, they had much more significant wind and wave forces on here, and then you had the tide going against the wind caused the seas to stack. And it started to drag these anchors. And when you start to drag these anchors, the bridge starts to go out of alignment and it loses its support.
At this point, another part of the bridge became a problem: the walls on the sides of the maintenance deck.
On the top deck, there was these barriers added on there for safety of the workers. Well, it wasn't anticipated that the water would come on so rapidly that the water couldn't drain through the drains fast enough, and it actually filled between the barriers.
All that trapped water began to find its way through the maintenance hatches.
These hatches were larger hatches that really weren't designed for real high pressures because it wasn't anticipated.
The pressure burst the hatches, allowing water to flood into the pontoons.
You get more water in your pontoons, you start to lose flotation, you get top heavy, you lose your transverse support, and the bridge started developing cracks, and then so it's a progressive failure.
The final straw in this epic fail came when the cables connecting the pontoons to their underwater anchors finally snapped. The Hood Canal Bridge may have been underwater, but leaving local communities cut off wasn't an option. A new bridge had to be built, and this time it had to be able to survive whatever Mother Nature could throw at it. State engineer Patrick Clark helped rebuild the bridge.
We're confident that the new design addresses those storm loads that we saw in 1979. The anchors were made much larger.
The new anchors are 3 stories tall and 46 feet. That's nearly 15 meters wide. They're basically vast buckets filled with rocks.
Each pontoon now has 3 anchors attached by cables twice as thick as those on the wrecked bridge. In addition, the new maintenance hatches are now firmly watertight, so the maintenance decks are no longer an issue.
The solid concrete barriers were removed and they were replaced with cable rails. The new bridge should be able to survive those kinds of storms. That's what it was designed for.
The fix cost $150 million, and in 1982 the bridge reopened stronger than ever.
Once the Hood Canal Bridge was rebuilt, we all celebrated because we did a lot of traveling that way, and it was just a great relief to everybody.
Here it's clear that engineers learned their lessons really well. Anchors that couldn't drag, stronger cables, submarine-grade hatches. The list goes on and makes you pretty confident that this bridge isn't going to be caught by surprise again.
Engineers always want to be ahead of the game, but with new innovations and technologies come new risks. Sometimes the gamble doesn't pay off. Like this disaster in Connecticut, where grand plans for a city's revival came crashing down to earth.
This came within hours of being one of the biggest calamities in the history of American structural engineering.
This lucky escape for a stadium full of people highlighted the limitations of computer-aided design.
Computer analysis designed to keep the building safe actually put thousands of lives at risk.
A very lucky escape for a stadium full of people.
Hours later, it was no more. And I don't know if I've ever really gotten over that.
Hartford, Connecticut, founded in 1635, is one of the oldest cities in America.
Hartford has the oldest public art museum and the longest-running newspaper in the U.S. Mark Twain wrote his classic adventures of Huckleberry Finn here. The town has a rich history, but in the 1970s, it had fallen on hard times.
Redevelopment was seen as a way out of the urban decay in the hope of reviving this once great and historic city. In the early 70s, 4 major projects were greenlit, and the centerpiece was a brand new stadium. the 10,000-seater Hartford Civic Center. Local journalist Tim Jensen explains how the stadium hoped to reinvigorate the town.
In the mid to late 70s, the Civic Center was not only the place to go for exciting sports action, but also it was the major concert venue between Boston and New York. Superstars from around the world performing in concert right here in the capital city of Hartford.
To embody this newfound optimism, the roof of the Civic Center would also be a superstar structure, using new and cutting-edge technology.
The icing on the cake was a state-of-the-art roof designed using what was, at the time, pioneering technology, computer-aided design, or CAD.
These days, CAD is used to design everything from household objects to spacecraft. But in the early 1970s, it was in its infancy.
CAD allowed Hartford's engineers to come up with an innovative new support structure for the 90 by 110 meter roof called a space frame. Structural engineer Stephen Ressler explains.
This model is a representation of the structural system that was used for the Hartford Civic Center roof. As you can see, those individual pyramid-shaped modules were tied together with structural connections in order to make this more elaborate, geometrically complex structural system.
The structure used 2,300 steel trusses connected to form a series of inverted pyramids designed to evenly distribute the weight of the roof. For added strength, the whole roof was supported by steel cross-sections known as bracing.
They did that in the form of these diagonal elements that intersect the top chord members right at their midpoints. By adding these diagonal members that frame into the top chord, they caused it to be, at least in theory, 4 times stronger than it would have been without these diagonal braces.
To save time and keep workers safe, the entire roof was built on the ground and then jacked up about 80 feet or 25 meters into the air.
The roof was the size of 2 football fields, and yet it was supported by just 4 pylons. It really was an engineering marvel and gave everyone in the crowd an unobstructed view of the action.
The cutting-edge new stadium opened in early 1975, attracting large crowds to music and sporting events. January the 18th, 1978 was no exception.
A huge college basketball game was played. The University of Massachusetts visited the University of Connecticut. Over 5,000 excited fans found their way to the Civic Center that evening.
Little did they know a disaster was about to unravel. A huge snowstorm descended on Hartford. Suddenly, the entire roof of the Civic Center collapsed. 1,400 tons of twisted steel and concrete fell onto the 10,000 seats below. Thankfully, it was after 4 o'clock in the morning and the building was empty.
It's lucky that this happened in the middle of the night. Just 6 hours earlier, the stadium was packed with 5,000 people watching a basketball game. Who knows how many could have been killed?
No one was hurt in the catastrophe. But what had caused the cutting-edge computer-aided design to collapse? In the days that followed the Hartford Civic Center disaster, young engineer Jeffrey Coleman was sent to assess the wreckage.
My first view was from the hotel next door. The roof structure was all twisted and wrapped together in various directions. It was a twisted mess. Buildings aren't supposed to fall down. And here I was standing in the midst of an incredible tangled wreckage. I was 24 years old at the time, and it was a real sobering experience.
Jeffrey looked at the obvious culprit, the snow, but something didn't add up.
At the time, the building code would have required the roof to carry 30 pounds per square foot of snow load. Live load, we call it. At the time it collapsed was 26 pounds per square foot of snow load. So the roof collapsed at a load less than what it was designed to withstand.
An official investigation found that the computer calculations had seriously underestimated the weight that the roof could handle.
When you look at engineering failures, you'll often find a well-intentioned decision followed by an unintended consequence. And that was the case here.
A computer model is effectively just a very fancy calculator. You get an answer based on the data that you put in. It's how those results translated into the real world that appears to have been the problem.
When entering the data into the computer program, engineers had failed to recalculate their numbers after a change was made in the original design.
The computer had calculated a design based on a flat roof, but the roof had to be slightly pitched so that water, or in this case snow, could drain off.
Flat roofs have an unfortunate characteristic of collecting water. The water pools, and that adds considerable weight to the roof and also causes drainage problems and leaks. And so the designers had to provide just a little bit of camber on the roof, an outward slope that would cause the water to drain outward. The designers added these small posts at each of the joints, and then the roof deck was built as a series of panels that were then placed on top of those short posts. Unfortunately, those posts ended up being part of the problem associated with the collapse of the structural system.
The dimensions of the new posts were not fed into the CAD system, meaning the computer's calculations were inaccurate.
By raising that roof up, those stubs no longer adequately braced that top chord in the horizontal direction.
As they lifted the now sloping roof into place, there were signs that it was struggling to cope. Under the weight of water or snow, this state-of-the-art structure was visibly sagging.
The deflection, or basically sag of the roof, was double what was expected. It would seem a clear warning that the structure wasn't behaving as the computer had predicted.
Despite all these warning signs, the designers continued to insist that there was absolutely no problem with the design and that they had the ultimate confidence in their computer analysis results.
When construction workers and spectators can see that the roof is sagging, maybe it's time to turn off the computer and get out the calculator.
The engineers' faith in the computer calculations caused them to doubt the evidence in front of their eyes.
The changing shape of the roof, once it had been installed, hadn't been taken into account and wasn't something the computer had been asked to calculate either. It turns out this made the roof highly susceptible to buckling.
While the bracing in the center of the structure was still strong, the warped roof had critically weakened the side bracing.
Because of the design deficiency associated with the lack of proper bracing on the exterior compression members of the space truss, these members were severely overloaded, and under that snow, they buckled like this, causing a transfer of load to the adjacent module and the chain reaction buckling of all the adjacent top chord members. This.
This triggered a cascade effect, buckling yet more members until the whole lot came crashing down.
In the wake of the 1978 Hartford Civic Center disaster, the city's mayor promised to rebuild the Colosseum, bigger, better, and crucially stronger. Today, even the heaviest snowfall is no match for the new and improved roof.
We actually designed the roof structure to withstand 35 pounds per square foot of snow load, as opposed to the code required 30. So we increased the load just to give everybody a comfort level in that regard.
The entire process of designing and constructing the new roof took just 21 months. And on October the 15th, 1979, the Hartford Civic Center was reopened and back in business.
The design might not be as clever, creative, or cutting edge, but the Colosseum's new roof has been built to last and is still going strong after 40 years.
I haven't been up here in 40 years. Looking down from this vantage point, you can see the seats where the spectators would be. You could see the arena, and you can imagine thousands and thousands of pounds of structural steel descending on those people.
One of the most important lessons that we as engineers have learned from the failure of the Hartford Civic Center roof system is that even while the computer is an extraordinarily powerful tool that gives us capabilities that we simply wouldn't have if we had to do our calculations manually, we must always have to apply common sense and good engineering judgment in order to ensure that the results we're getting from the computer actually translate into safe structures on the ground.
If heavy snow ever hits this roof again, all sports fans need to worry about is keeping their eyes on the game.
When engineering goes wrong, the cause can be staring us right in the face. But sometimes there can be more to a fail than meets the eye. Like this dam in the mountains of Wales, and a disaster that went down in history.
This dam was doomed from the very start.
You can hardly imagine the scene in the valley with the remains of the dam.
An engineering fail that destroyed a village.
This catastrophic failure forced a change in the regulations.
Wales is a rugged land. Its mountains and streams are rich with myths and legends.
Wales is known for ancient Celtic folklore, grand castles, and natural beauty. But there's another side to the country. It's long been an industrial powerhouse.
A driving force behind all this industry comes from the mountains, as the rivers flow to the sea. A century ago, to harness that untapped energy, engineers started building dams to feed hydroelectric power stations, like this one in the village of Dolgarog. Geologist Jonathan Wilkins explains.
This is a good location for the generation of electricity because the terrain gives a very, very rapid drop in height between the reservoir and the floor of the valley where the power station is situated. Well, this is the generating hall from Dolgarog Power Station. In front of you, the large blue pipes are bringing water from the reservoirs, and the big square boxes are the alternators which are supplying power to the national grid.
Key to a constant supply of electricity was a large reservoir of water. First built in 1924, the 120-metre-long Coty Dam held back millions of gallons of water, which was used to power a nearby aluminium works. But just a year later, disaster struck. In the autumn of 1925, North Wales experienced unusually heavy rain, putting a massive strain on the Coty Dam. But no one was prepared for what happened next. Dolgarog resident Daffyd Williams knows the story well.
There'd been raining for several days. Water was sort of accumulating on the dam above the village, and then later on that night, the dam burst, bringing thousands and thousands of gallons of water down.
The water gushed over the dam's crest, and although no one in the village knew it, the dam was minutes from total failure.
Suddenly, the Coty Dam collapsed, sending a raging torrent into Dolgarog.
Right now we're standing in the path of where the boulders and the water came down, bringing 1.74 million cubic meters of water. Nothing had any hopes of surviving in all this.
In an attempt to warn the villagers, the church bell was rung 3 times, but it was too late.
The flood quickly overwhelmed the village, carrying debris, including huge boulders that weighed hundreds of tons.
This is one of the boulders that came down that night. I'm about 5'9", and this is not the biggest of them. This is small comparison to some of them.
The result was completely devastating to the village and to its inhabitants.
This is the piece of pipe that came down with it. As you can see, it's all crushed. You can see how it's mangled up. You can imagine if the boulders can do that to a piece of metal like that, what we do to buildings and people living there.
Tragically, 16 villagers lost their lives, including 6 children. Engineers had to figure out what had gone wrong and how to protect the villagers from future tragedy. As the floodwaters receded from the village of Dolgarog, it was clear that the Coty Dam had failed. But engineers soon discovered the real cause of the tragedy lay upstream.
The Coty Dam wasn't the only dam in the system. There was another, older structure further up the mountain, the AGI Dam. At the time, it was used to regulate flow into the reservoir downstream, and it was this dam that had failed first.
But what had caused the Agi Dam, built only 14 years earlier, to collapse so catastrophically? Author John Lawson-Riea believes it's all down to the construction.
It's absolutely rubbish. The construction of it is dreadful. And they were always patching it up. And you can see the patches here, some of the patches. It's rubbish. It just falls apart. And it's no wonder that it was causing problems.
One key error was in the foundations. In the original construction, it seems these hadn't been dug down to the bedrock.
You have to remember, this dam was built more than 100 years ago, so engineering knowledge was nothing like it is now. But with foundations that didn't reach the bedrock, this dam was destined to fail at some point.
We're coming up here to the place where the wall had been breached. There'd been a washout underneath it where the undermining of the dam would have taken place. That this had caused the dam wall to actually collapse at a major force, sending billions of gallons of water down into the valley to the Coity Dam. Now, Coity Dam was just a headstock. It was not intended to take a large quantity of water.
As the water spilled uncontrollably downhill, it gushed into the Coity Dam, overlooking Dolgarog, and the dam overflowed, known as overtopping.
When a dam overtops, it's game over. Once water hits the downstream side, it can be a matter of hours before a total collapse.
As local geologist Jonathan Wilkins explains.
The water rushing across would have poured into the valley, eroded the downstream side of the dam, and once the erosion of the downstream side of the dam was severe, the concrete itself would have been exposed and weakened and liable to failure. At that point, you can hardly imagine the scene in the valley with the remains of the dam and all of the debris, the floodwater, rushing down the quite narrow river valley, down quite a significant gorge in the trees which you can see in the distance.
With both the Agi and Coity dams destroyed, there was only one solution.
The Coity Reservoir was fairly quickly repaired because its design was sound. It had simply been overwhelmed by the water that arrived from the Agi Dam. The Agi Dam was never rebuilt because I think it was realised that the design was fatally flawed. In order to make the Coity Dam safe, they installed spillways and ways of handling water which came over the crest of the dam in a way that did not lead to erosion of the downstream side of the dam.
Tragedies like this highlight engineering oversights. The crucial thing is that engineers learn from these mistakes so that new structures can be stronger and safer.
Today, the Coity Dam stands solid, both generating valuable hydroelectric power and protecting the village of Dolgarog from another catastrophe. The events of 1925 will always be remembered.
This is a memorial we set up to remember that night with the names of the people who lost their lives. A lot of the villagers still come here and to remember it, very emotional about it. They can come here and they can sort of ring the bell to remember what happened that fateful night, you know, when the church bell was being washed down by the river. The only good thing that came out of this, that new legislation came out on dam building and dam inspections.
The disaster led to the Reservoirs Act of 1930, which changed the rules when it came to dam construction and safety in the UK.
If there is any consolation here, it is that the investigations into Dolgarog led to big changes in dam safety. Since the disaster, there has never been any loss of life due to dam failure across the UK.